the October stream processing. We have a couple of talks today, actually 3 talks. But first, let's go through some administrative stuff. This is our schedule for today. We'll talk about it in a second. All these talks will be recorded and available on YouTube later. The link will be shared in the Meetup. If you have a question, you have to go through, you cannot unmute yourself, so you have to go through Q&A. Just click on Q&A and add your question. At the end of the talk, somebody from here will read your question to the presenters. If you have any questions or you want to present, just post a message on the Meetup site or send email to the emails here. This is us. And we'll get back to you on this. All right, so let's start. The first talk, it's visually debugging Flink incidents, Flink in 3D, and it will be presented by Colton Pilgrim and Mitch Gray. So Mitch Gray is a software engineer or solution engineer in Detorius, and Colton is a Detorius Flink advisor. He's been an invested user of Flink framework for past 4 years in both the transportation industry and now in EdTech space at Hulu. He comes to the table with 9 years of data engineering experience, but has been tinkering in various programming spaces for the past 15 years. Colton being a key member of the teams he worked with from designing, implementing, and troubleshooting a whole host of Flink pipelines. So welcome. I'll stop sharing so Colton can start sharing.
All righty, can everyone see the screen?
Yeah, we can see it.
All right.
Can you hear me now? Perfect.
Can hear you.
Awesome. So good afternoon, evening. I'm Mitchell Gray. I'm a solutions engineer at Detorius, which is an observability platform for Apache Flink. I'm a software engineer that turned solutions engineer or sales engineer, and I've been working for Detorius for about 1.5 years. Joining me today is Colton Pilgrim. Colton, you want to introduce yourself?
Yeah, hi. Actually, I've had a pretty good introduction given to me. But yeah, my name is Colton Pilgrim. I'm the Flink expert here at Detorius. And as I said, my daytime job, I work over the ad platform team for Hulu, making sure that all those ads you see get built.
Perfect. Colton, can you try to change the slide?
Yeah, sure.
Perfect. All right, so for the agenda for today is to look at a fresh approach to identifying root causes and diagnosing complex problems in Flink, one that's faster and more user-friendly. So what we'll cover today is the need for visualization and why seeing is believing. And we'll go to why visualizing Flink problems is different and more complicated, and the use cases for unlocking faster diagnosis with data visualization. And then we'll save some time at the end for questions, if anybody has any. So let's go ahead and jump in. And before we do, let's talk about something fundamental. Why is visualization so crucial for understanding and diagnosing problems? So let's try to take a quick experiment. By show of hands, and I don't know if anybody wants to show hands on video online, how many people think that global warming is a real problem? Couple? We got questions for the rest of you? So let's see, if we look at this graph here, let's take a look. At first glance, you can probably tell that something is happening here. There are trends, spikes, a lot of data points. But if I asked you quickly to explain what's going on, could you? It's packed with information, but not exactly clear what. It's the kind of graph that makes you feel like you're missing the punchline. So let's take another example. So this is a short video of global temperature trends by country over the last 100 years. So if you look at the graph, the blue ones are below 0 and the red ones are above 0. As we watch this video, you can see how the time moves forward and the temps start to rise. If we look at the 80s coming up, you'll start seeing it getting more red all the way up until 2020. Unlike the last graph that we were buried in a sea of data, this video distills decades of information in a clear visual story. So I ask again, after seeing this video, how many of you feel confident that global warming is a real problem? A couple more hands. So you can see the difference. When we just looked at the raw data, it's hard to get a clear picture. But once we turn it into a simple visual narrative, the message becomes much clearer. It's not just about presenting the data, it's about telling the story behind it. The challenges with data is that it's often overwhelming. In systems like Flink, there's so much data, logs, metrics, events, it's hard to make sense of it. Without a story to guide us, data can feel like noise. We need to take the data and turn it into something that is easy to follow and meaningful. So how can this be done? The answer is data storytelling. Data storytelling is the process of turning raw data into a meaningful and actionable narrative. It's not just about showing numbers or charts, it's about making the data understandable, relatable, and insightful. It combines three key elements. If you look up at the graph, data, which is the facts, the numbers, the trends that provide the foundation. The narrative, which is the story that gives the data context and the meaning. And visualization, which visualizes and brings data to life and makes the story clear. A good data story should simplify the complexity. It should break down complex data into something easy to understand. Engage the audience and make it relatable so the audience connects with the story and finally guides the decisions. It should help people make the decisions based on the story that you're telling. A great data story doesn't just show the data, it shows what the data means and what actions to take next. Diagnosing failures in Flink is not exactly straightforward. It requires more than just logs or metrics because some of the unique challenges that come with stream processing. Let's explore the three key reasons why understanding or reproducing failures in Flink can be so difficult. The first challenge is that Flink often processes data out of order. Events do not always arrive in the same sequence they were generated. So when you're trying to figure out what went wrong, it's crucial to the process that data is in the exact same order it was originally received. Without doing that, it's nearly impossible to accurately recreate the issue. The next challenge is time. Time plays a crucial role in Flink stream processing. The processing time and the order in which it was processed can significantly affect the outcome. A record could end up in a different window, be ignored due to latency policies, or be counted as a late arrival, which might trigger additional actions and consume more resources. This can even lead to a different final result. Without reproducing the exact timing, it's tough to understand what really went wrong. The last challenge with Flink is the state is hidden. Each record interacts with and affects the state, but there's no way to see how or understand what's being stored at any given moment. Without visibility seeing into what is in your state, it becomes very difficult to pinpoint how specific records contributed to the failure. So let's review some real use cases in some scenarios in real life. Colton, you want to show these use cases?
Yeah, sure. So 1 second, I'll actually move over to my side. So let's get into the juicy stuff. The real world problems that we've encountered with Flink. These problems can happen to any of us, from the beginner to the expert. Our first use case is the dreaded late data. This one's a headache that it's drilled into us like from day one. If you pick up an O'Reilly book, you're going to see it on the first probably 100 pages of the book, and then many, many times throughout the Flink documentation. Our second use case is runaway or unpurged state. This one's a doozy, especially if you're writing stateful process functions or custom window triggers. And then our use case number 3 is incorrectly updating state. And I'll admit, this one's on us as an engineer. We're at fault here, but it still makes us question our lives as engineers when we have to debug these. All right, use case number 1, late data. So I know what you're probably all thinking, Colton, we know about late data, we handle it all the time. However, it's still one of the most common problems I see new Flink engineers face. The whole concept of 2 different time systems and watermarking is tough to wrap your heads around. So what is late data? Late data is pretty much exactly what it sounds like. It's data that made it to your Flink pipeline too late and cannot be processed like on-time data. This occurs when 4 criteria are met. You've assigned events to non-processing time-based watermarks. You're using a bounded out-of-orderedness watermark strategy. You've made a window somewhere in your pipeline that is using event time windows, tumbling or sliding or sessions. And then you have data that goes back further than the time that's allowed by your out-of-orderedness on your watermarking strategy. So how does this affect our output results? So this leads to data being unaccounted for in your window emits. This causes inaccurate results that might affect your revenue And ultimately, the trust in your data. The problem here is it's also kind of silent by default. If you're not checking if you're receiving late data, the problem's going to go unnoticed. So how do we become actionable, and how do we even know this is happening? So first thing we can do is we can create some custom metrics on our late data side output. We can regularly investigate data latency. We can also have conversations with your upstream sources. So thing is, once ever you've started, using Tutorials and you have the telemetry collector up and running, you can come and actually look at your job and see, what's going on in your job. So you have here is a breakdown of all the operators that you have in your job graph, how many records that were sent and received from them. But the thing is, we're actually more interested down here in this window collector. So as you can see, this pipeline had 60% of ignored records. Not great. Definitely wouldn't trust this data source. That's actually a pretty big chunk of data. So we're probably going to have a conversation with our upstreams to see if we can come up with a better data latency rules compared to what we're given. However, we can actually click on this percentage to get a list of each of the ignored events that ever passed through our job. So you can see the processing time of whenever it was ignored, the event time of the actual event, and also the key that it affected. These screens are super helpful for verifying if we're seeing late data, but it also helps us in figuring out which potential records were affected. The best part about this is it actually requires no user code on our end, and we don't even need to set up metrics or handle the data in any special way. We kind of get this out of the box with the Tutorials telemetry collector. So from here, we can show our ignored records. If you click this little checkbox, and you can see on this timeline down here, it's a lot of red. And that means that every single one of these records were missed. So we can get a little more insight to our late data by looking at the job insight screen by selecting it on the left, which is over here. So all right, now we can see our windows. We can see this one only has one emit. It's kind of not great. The thing is, we were expecting to get data, I think it was like once every 5 seconds. So that means we'd have 12 records in here, only one. So as you can see, I wouldn't trust this data. Now on to our slightly more tricky use case number 2, runaway state. Unpurged state, and sometimes it's also just state that's too large. So what is runaway state? Runaway state's when the state that's held by your Flink pipelines becomes too large to be kept in memory, or if you have RocksDB enabled, you can also spill over into disk. There are several reasons you might encounter a runaway state. The data you're ingesting is simply too large to handle with the state values that you want to store. You're storing too much data in state, or you're storing like a large list state that should have been reduced down in each event coming in. Or the biggest one that I see more often is that engineers forget to clean up their state after they've started using it, or after they finished using it. So how does this affect our output results? Well, the scary part here is that having runaway state can actually lead to out-of-memory issues. This means that your pipeline is going to halt entirely until you either scaled up the cluster or you manually intervene to push changes to your pipeline to handle this problem. In the end, this is a show-stopping problem. Your pipeline will cease to emit anything until the problem has been handled. So how do we even know if it's happening to us, and how do we mitigate this problem? Well, I kind of give you the answer with the last one. So we know that it's happening if we see an upspike in out-of-memory errors. The issue here is that out-of-memory errors can happen, for a whole host of reasons. So we don't know if it's runaway state or simply just state size is too large. There's also not a great way to track state size using metric reporters. So to become actionable on runaway state, you have to rely on half-baked solutions like looking at your managed memory utilization, which doesn't exactly point to runaway state, or you have to create custom metrics to calculate the size of the things that you're storing in state. This one's kind of costly to our performance. So what we really need is a way to view our state. And thankfully, this is something we can do now. So we've got our different job loaded up. We'll hear back the tracer screen. This pipeline is supposed to calculate the minimum, maximum, and average statistics for each temperature sensor every time a new sensor reading is sent. This is a fairly easy calculation, but I think the way that was implemented here is causing a runaway state. So what we're seeing is this job started up. After a bit, it eventually hit an out-of-memory error. And this happens no matter how many times we scale up the memory on our cluster. So how do we check if runaway state is a problem? It's pretty easy. So first thing you're gonna do is go to the last record and for this operator before the pipeline crashed. And the state we want to query is the temperature readings. So what we presented here is the incoming records in the middle. And on the left, you have the state before the record was affecting the state. And on the right, you have what the state values looked like afterwards. So in our incoming record, we can see that the reading was 30. So if we scroll down here to the bottom of both of our state values, so beforehand, you can see that the last stored state was 36. Then afterwards, it was 30. So that means that basically we got this incoming record and it just appended this to this list state. And then it calculated the, the minimum, maximum, average over all of the ever like received events. This isn't great because, it's very inefficient. You could have just reduced this and kept a very small state for this operator. There's no, there's no like, telling like why we were getting these out of memory errors. Our state was just going to grow infinitely. And then for our final use case, we're going to talk about is incorrect state updates. So this one's a little bit different than the previous two because it's actually directly caused by us as the engineer. I actually even made the same mistake when I was writing a different pipeline just a couple of weeks ago. So, but how often does it happen to you that you're kind of writing a process function, we think we covered all our bases, only to find out we didn't. So, or maybe it wasn't even our problem to begin with. Maybe upstream changed the data schema and didn't tell us. So now we're handling new state cases we didn't know about. So, what is the problem and how does it connect to us? Incorrect state updates is just what we think of when we should be updating state, but we didn't. Maybe we should be updating or purging state when we shouldn't. This is normally fairly easy to unit test with test harnesses, but becomes more tricky when you start chaining operators together. So how does it affect our output results? Well, with this use case, there are many different ways it could affect our results. You could either be storing too much or too little state in our outputs, or there could be a use case like where you're trying to broadcast data across a stream, and then you no longer have the records and broadcasts that you thought that you were going to have. Maybe we're forgetting to update a value state, holding our registered timers. So now we're not actually cleaning up state, and that could actually look like a runaway state problem. The thing is, it could also be silent, and it could look like our late data problem. The possibilities here are kind of endless. So how do we know if this problem is even happening, and how do we become actionable on it? Debugging these issues can often be tough without being able to see how our state was updated in the pipeline. Most of the time, there's no way to monitor these situations, so it kind of requires some manual verification of the output. And the best way to become actionable is actually to have good communication with your upstream sources and thoroughly review your pipeline's code, to make sure you're handling all your edge cases. Well, so I'm going to show you the pipeline that I messed up on when I was writing a couple weeks ago. So what happened was I'd sent this pipeline off to verification by our CO, Ronan Corman. And he went to go start looking through it. He opened up a record. He was like, "Hey, Colton." He was like, "Shouldn't there be, a value for timer state?" He's like, "Is there something wrong with our product, or is there something wrong with your code?" And yeah, it was me. Yeah, there should be a timer state update there, and also registering the event time timer. But that's business. And I even have receipts. This one was on me. All right, back to you, Mitch.
Perfect. Let's wrap this up and we'll take some questions. So a couple of key takeaways. First, visibility is the key. Flink state and timing are hidden by default, and you need tools that provide you visibility into how data is processed and stored to understand what's happening inside the system. Second point is that state and time drive Flink challenges. The core issues in Flink originate from how it handles state and time. Solving these problems requires real-time insights. Third is data correlation and storytelling. Great observability tools connect the dots and tell the full story. Our platform correlates logs, metric, and traces in a single narrative. And lastly, speed matters. Diagnosing Flink issues manually can take days. It can be super frustrating. We've all been there. But with the right tools, it takes only minutes to solve these complex problems. Any other questions, or does anybody feel different about climate change now? Anybody online? Any questions?
There's a question online. Raj Singh asks, for late message detection, how is time synchronized across servers in the cluster? What time synchronization solution is used? Have you ever experienced time drift where a Flink processor encounters a message which to the processor looks like it is from the future?
Okay, so actually, like Flink, everything happens in one cluster. So whenever you're, applying your watermarks, you can either do processing time watermarks, which just uses the watermark or like the time of the system. But then you also have like event time watermarks where you supply a event that's happening like inside of your event. Um, and you normally you have to like supply some sort of like, bounds around this. So like if you like want to accept data that's like 5 minutes out of order, then like your data's delayed by 5 minutes. But in terms of if I ever experienced time drift, like where like a Flink processor encounters a message that looks like it's from the future, no, not in like a real use case, but like if someone was ever to, send a message inside of, whatever I'm reading from like Kafka Kinesis, and it has a timestamp that's from the future, then that's going to be a problem because it's actually going to advance the watermark forward, and then it's going to ignore all the records. So like say it was 15 minutes in the head that they put that event timestamp, then now I'm going to miss 15 minutes worth of data, and that's kind of a big issue.
All right, thanks, Colton.
Any other questions?
I have a question. How does the tourist access the pipeline? How do you get access? How do you know which events are late? How do you know how to read the state? Is it running as a library or is it running on top of it? How do you access those?
It's running with Flink, so essentially we'll give you a customized version of Flink. Whether you're running like Docker or Kubernetes, we'll give you a customized version. You don't have to have any code changes. You're just running essentially native Flink with us in it, and then you have access to everything. You don't have to like add log lines or write any code.
Okay, thank you.
The question back there?
Hey, so I have a question. What is the storage backend for all your data that you show here?
How large?
Yeah,
Theoretically, we don't have a limit. Obviously, you might run out of screen real estate at some point if it's massive. We're looking at some ways to maybe condense that and allow you to expand. Are you worried about performance maybe?
so is it a remote store or is it in process?
Colton?
Oh, I think he's asking like where are we actually storing the data? It's so there's a telemetry collector that exports the data over to the Torios's API. We also have one that can run in your cluster as well. Just depends on how you want to set it up.
Thank you.
Any other questions? No, anybody else online?
I don't see any questions in the Q&A.
Awesome, appreciate it, guys.
All right, thank you very much. The next talk is from Stream Native, Ursa, Kafka-compatible data streaming on Lakehouse. The presenter is Matteo. He's the CTO of the Stream Native, where he brings rich experience on distributed PubSub messaging platforms. Matteo was one of the co-creators of Apache Pulsar during his time at Yahoo. Matteo worked to create global distributed messaging system for Yahoo, which would later become Apache Pulsar. Matteo also co-founded Streamlio and later served as the senior principal software engineer at Splunk post-acquisition. Matteo is PMC chair of Apache Pulsar, where he helps to guide the community and ensure the success of the Pulsar project. He also PMC member of Apache Bookkeeper. All right.
Hello, everyone. Hi. So yes, today we are going to be talking about Ursa, Kafka-compatible data streaming on Lakehouse, based on Lakehouse. And thank you for the interaction already. So Maria and Studio is Simnative, and mostly working on Apache Ursa for many years now. And Simnative itself is a company that offers services on top of Apache Ursa. It's a product, data streaming product that is based on Apache Ursa. And we're going to start today with talking about what is Ursa and why Ursa. And before getting into what Ursa is, I want to start from like kind of like taking out the elephant in the room here, since we are in LinkedIn, and talk about Kafka. So the first thing is that Kafka API has become ubiquitous. It is everywhere, and it is something that one has to deal with. But the implementation is not ideal, and there are multiple inefficiencies, multiple ways that current implementation, both open source as well as closed source, are not well suited for many use cases. Might work, but might not be the best option. And if you look at the many products, many of them come from the architecture of Kafka, and it's kind of like the tying up the compute and the storage for Kafka leads to that you have to kind of like over provision the cluster in order to support big traffic. You cannot easily scale up and down because the data is tied to a single node. So and then you have all these problems with data rebalancing, partition rebalancing. You want to scale up the cluster, you have to copy data. It takes all the time. It takes a big toll on the cluster operations. There's massive cost on cost for cross-Z network usage for data replication and data rebalancing. And this is kind of like a problem that comes out with more and more people using cloud as the native environment for all the applications. And finally, like again, this is kind of like a first like a high-level bullet points, but it is very expensive to store long-term data into local disk. It is not competitive with the cost of object storage. So in Simnative, we have been kind of like seeing a lot of use cases, a lot of different problems in the architecture for messaging and streaming, and we come up with the Ursa. And Ursa is the engine that powers our cloud products. And if you look at what we're trying to achieve with the Ursa is kind of like the first tenets of what like the philosophy of design. And the first one was to be protocol agnostic. We want our platform to support multiple protocols. It can be Kafka, it can be Ursa, it can be MQTT, it can be MQP, and so on. We want to give them the biggest flexibility to user so that they can port their application, use different semantics on top of our platform. Second tenet is around the storage. And I think it's clear right now that having proprietary formats, even if they're open source, if they're not really easily usable by all the tools, they're not flexible enough. So the storage needs to be using open standards, such in a way that can be easily reused and easily accessed from multiple tools and visualization and analytical tools and so on. And third one is flexibility, supporting a wide range of use cases. There are some cases that are like very strict on durability and latency, and some cases that are very strict in cost, like a massive volume of data, but the data is not very, the single event is not very important. If you look at log ingestion, is like a massive volume, but if you miss some logs, that's not the end of the world. But if you're looking for like a payment system, losing data is very important, and the latency is very important. So there is a wide really set of different requirements so that we want to target that. And the fourth one is kind of like bringing it all together and redesign and rethink a bit the whole system, applying modern architecture principle that can satisfy all the requirements, and do that in a way that is easily operable and cost effective, and yeah, the holiday. So Ursa is we call it a Kafka-compatible that's streaming on Lakehouse, and it is based on Apache Ursa, but we kind of like recreated a bunch of components inside and out. It is Kafka API compatible, so you can use any existing Kafka applications, from the simplest one to the most complex one. We support all the features like transaction compaction and everything in between. But we don't just support Kafka API, we also support Ursa API, of course, and MQTT and others. We have evolved the process storage layer to be using persistent the data stream directly in Lakehouse format. And that's important because Lakehouse is becoming more and more standard. There are different formats there that we support, but it is kind of the preferred way for people that I want to consume my data as a stream, but I also want to consume it doing like a batch analytics top of the same data with the minimal delay possible. And finally, it is kind of like implemented as no keepers, the catchy term, but bookkeeper becomes optional at this point. So also storage was historically based on bookkeeper and was also using Zookeeper for metadata. So, but we have eliminated all the keepers. So Zookeeper is not needed anymore. Bookkeeper, it is optional if you want low latency, but it's not required. Going on. So, and we discussed about Kafka implementation that couples storage and compute. And the easiest way to see it is that each broker will have the same data for the partition, so that you cannot add one more broker because it'd be empty. So you have to copy partition data and so on. And so that it is kind of like architectural limit that kind of like impose on an operational limit. Now you cannot scale a cluster up and down. We can do that with Pulsar and Ursa. But so the answer to that is separate compute from storage, and that removes the problem of the data rebalancing. And if you look at it, Pulsar from the very beginning, when it was first open source, it was architected in this way. So you have brokers which are stateless, or they don't have any durable state. The state is kept in storage and metadata, and then you have the bookies, and the bookie represent the storage layer. I remember like having many discussions with people in LinkedIn many years ago around, yeah, but now you have one extra copy of the network of the data, and in the end, my argument was that it's not that important. So it is not as bad as having your architecture as monolithic, right? Because what gives you this decoupling, this logical decoupling, it doesn't need more resources. It just allows you to scale this two layer independently first. But more importantly is that if you need more storage, you just add more storage nodes, and then naturally will getting more load. And same for broker. We can easily rebalance traffic without copying any data. And depending on hourly peaks, for example, like if a topic becomes very hot because there's a sudden spike in traffic, we can easily move this topic to the other brokers. And so you can see that this keeper as a kind of like this layer of a storage write-ahead log and segments of data. So what gives you this? It is instant elastic scalability, and you don't have to over provision. Also, like we run auto scaling, in our cluster in production for a lot of time already. So we can add more brokers, we can add more bookies, and scale up and scale down depending on the current traffic, and doing that multiple times a day. The next logical thinking there was like in 2018. Actually, we started it. Okay, I want to store a lot of data, and I don't want to pay to have storage nodes with CPUs and keep like EBS volumes or local volumes because it's very expensive. So what can we do? You can use object storage for that, and that's why we took the concept of tier storage. And actually, Ursa was the first system that kind of like introduced tier storage in the streaming world. So into the tier storage, which means that the hot data, the hot segments that are like the most recent ones are in Bookkeeper. But the data, as it ages up, it gets pushed to S3 or GCS to object storage. So what gives you is that you have removed the cost of local storage, and you don't have any upper boundary on the amount of data you want to store. And then think through that through the years. Again, this something that comes up in one day is like iterative process, right? So you see you put out these, people will use it, and then next question is, okay, I have all my data into tier storage in second tier in S3, but I cannot query directly because I can use it as a stream. I can go through the brokers and read everything, but I cannot run a bad job easily, right? Because it has to run through the broker always. And why can't I just read the data from S3? And the reason is that it is a proprietary format. Like we came up with some, again, it's open source, but we came up with the format there for the data to be in raw format as well, not columnar. And that's not ideal because people cannot make immediate use of that data that is S3 in the most efficient way, which will be to just go to S3. So the next question is, if it is there already in S3, why not just use a common format like Lakehouse format? So the next iteration was that, okay, we have a tier storage, but once we offload it, we offload it in a columnar format, and we can use Data Lake, Hoodie, or Heisberg. And so that was the next iteration there that we delivered that last year to our customers, and that was the first iteration. Then the next question was, okay, what why do we need to the hot segments versus the cold segments? Can we simplify the architecture here, and can we make it also more cost effective for use cases that don't care about low latency? So yes, so we support Data Lake in that. So I have these extra slides here. So the question there is that how can we optimize the system for cost and latency, and can we make it such that we can choose within the same cluster to prioritize for some topics the costs, or some topics the latency, and give the most flexibility. So if you have any OLTP use cases, you can go through low latency tier, and if you have any analytical workloads, you can just go through the low cost tier. And we came up with this. So this kind of like the core of the Ursa architecture essentially, but we can have two different kind of write-ahead logs. One write-ahead log is a traditional one using Bookkeeper that can give you low latency. We're talking about like in the order of like 2 milliseconds at the 99% latency on the published side. And the other one is using object storage for write-ahead log, in which case you can get latency mostly dictated by the object storage layer, which would be around like 250 milliseconds. And for S3, for example, and if you use S3 Express, you can get it down to like 20 milliseconds, kind of ballpark. So essentially, we give the option that you can choose within a single cluster how do you want to store data for this particular topic. Like putting everything together here, right? So you can see that we do have a different option. It's kind of like different modules that you can pick. So it is open at the protocol level. You can choose your own protocol. It is multi-tenants because Ursa architecture is inherited by tenants since the beginning. And then we have the option of cost optimized write-ahead log versus latency optimized. And then we have the option of the Lakehouse, so kind of like an open format throughout. So open protocol at the top and open storage format at the bottom. And so these new terms are actually going by CU here, and it's kind of like taking the old CAP theorem for consistency, availability, and partition resilience, and translating that into the cloud world, which is, and with different terms. So if you have CP, you optimize for cost and performance. So you can have low latency with a single zone deployment with Bookkeeper, but you lose the availability if that one zone goes down, or you can optimize for AP with availability and performance. So you can use Bookkeeper in multiple zone deployment. So you have low latency and availability but it will be more costly because you have to pay for the inter-Z cost. Or you can use CA, which is cost and availability. So you have multiple zone deployment using object storage with high latency but lower cost. And yeah, so the idea is that the only missing standard piece there is the write head log format. There is no suitable format for that component. So hopefully in the next months and years, something will come up. So, but we start with our own opinionated format for that. And in terms of timeline, so multiple components of this have been already delivered, starting from the Kafka API in January this year. That was G8, and then several other parts were like put in public preview in Q2, and the last bits that are right now in private preview, but they're going to be announced in public preview next week officially. It is the cookie removal and the cloud storage support. So these are the last pieces of the whole picture that are going to be made public on the next week or so. So actually, this I think is actually the most interesting part is how does Ursa work inside and what are the components there. And to start with, the first philosophical change here is that Ursa decouples method data operation from data operation. So these are kind of two different paths and two different components in a way. And that's very important because that gives us a lot of flexibility. So the first part is metadata operation. So metadata operations are served by Oxia, which is our metadata store. And I'll talk a bit more towards the end. So Oxia is being used here for coordination, for indexing to index all the data where it's stored, which object, which offset, and so on, and for transactions and so on. So all this coordination part is served by Oxia, and all data operations are served by object storage if you use the cost of optimized tier. So like all the write, append data, and read data go directly on the object storage side. So if you're looking in terms of architecture here, we kind of see that we kind of like create a library that works inside the Ursa broker and kind of like replace completely the storage of the Ursa broker. What that does is that kind of creates this abstraction of a stream and the storage of a stream, and that is implemented down in the implementation. We'll use write head log and we'll use all the compaction into Lakehouse format. So we say that okay, the first component is a Ursa broker, it's still the same, but with the storage layer completely swapped out. And the important thing to note here is that so traditionally on the Ursa broker, like one topic is served by one broker at one point in time. There is like a strong ownership of the topic. Now it can be moved very easily because there is no data there, but it is one point in time. It is owned by the stock for both writes and reads. We kind of like remove this constriction here. So right now, given the new architecture, we can actually have writers that can be writing on the same stream, on the same partition for multiple different brokers. And the idea, and also reads from different broker. The idea here is that you want to have a zone-aware traffic routing. So if you have a client that is on AZA, and you want that client to be talking to a broker in AZA, not in AZB, because otherwise we have to kind of cross the AZ network boundary. You have to pay 1 cent per gig, right? So it kind of like allows that flexibility that you will always be routed to a broker that is in your AZ. So the ownership becomes a bit more shared. It is not exclusive. So multiple brokers can own the topic in one cluster, one per AZ. And yes, we support multiple protocols from Kafka, MPT, and so on. The next part is the Ursa storage library. So this doesn't use any storage nodes, so it writes directly to the object storage, and then it updates the index in Oxia. So that is when the data becomes visible to the brokers and becomes visible for the consumers to read that data. And the semantic of this Ursa storage library are kind of very simple, but it's kind of append on a row base, append one entry or one batch of entries, or you can also append one Parquet file into the stream. So it's kind of like a columnar format append. And this kind of interjects an entire Parquet object into the stream. We get assigned an offset, so it's kind of like once it gets inserted into the stream, it is final. Like the ordering of the data, it is decided there. But this kind of gives a much more efficient and effective way to get a large amount of data into the stream directly. And then you have kind of read entries, truncate, and end the stream. So the kind of basic operation on the stream abstraction. So we say that this is kind of the same one. I repeat this. These. So I want to talk about a bit about the write-ahead log concept, right? So Ursa storage is based on the write-ahead log, and the write-ahead log is kind of like multiplexing data from multiple streams into a single physical write-ahead log. And once the data is in background, after a while, the data gets compacted, and now you can create, basically, it gets into the Lakehouse format and in columnar format, right? It gets compacted there, and then the write-ahead log is streamed. Now, write-ahead log seems kind of like an overcomplication here, but it's actually very important for the whole to have everything to make sense in a way, because it has kind of a few purposes for the write-ahead log. So the first one is to minimize the buffering and the latency. Like if you have, say, your traffic is spread across 10,000 streams, 10,000 partitions, and each partition has to do some buffering before writing to object storage. If you want to have any meaningful buffering, then you have to wait, say, 1 second, 2 seconds in order to have few entries, right? Now, if you have a single topic, single partition, then it's probably not needed because you don't need write-ahead log in that case. But if you have 10,000, then you absolutely need this kind of like multiplexing, because otherwise you end up either you have to wait many seconds before you can commit to object storage, in which case your latency is going to be terrible, or you have to use lower buffering, but making many tiny requests to object storage will become very expensive in terms of like put requests on the object storage. So it's kind of these dual requirements, right? So on one end, you want to make as little requests possible to object storage, but you also want to have low latency, like a reasonable low latency, right? If you're talking about 250 milliseconds, I don't want to wait 5 seconds for my publish request to be acknowledged. So this kind of a tool, right? By using a write-ahead log, we can make sure that we can group all together across these 10,000 topics, for example, and we'll have to wait the 5 seconds. We can just wait like maybe like 10 milliseconds or 100 milliseconds, and that's the only buffer we need there. And the other requirement of this decoupling that we don't write data directly into Lakehouse format is that, like Lakehouse, when you want to read the data out, it works well if the Parquet files are big. Now, again, it's a counter. These are two conflicting requirements, right? On one hand, you want low latency, that means low buffering. On the other one, you want to have big files to have like a high throughput for reads, which means that how can you do it? So by using the write-ahead log, we can decoupling the building of the Parquet file from when the data comes in. So the data comes in, it gets written into the write-ahead log, it gets synced there, it gets indexed, and now it is available. In background, we can take the write-ahead log and then compact it on the in Lakehouse format. We can wait 30 seconds. It can be 5 minutes. It can depend on each stream will have different requirements, right? On how soon you want the data to be available in Lakehouse format. But that doesn't affect on your publisher. Like the publisher will say 50 milliseconds latency, and that's it. So that's the longer explanation on why you need the write-ahead log. And on the implementation side, right? So basically, it's kind of visualization here of the write-ahead log, but essentially, like it's a sequence of objects in the object storage written by multiple brokers, and then the index are written into Oxia. So whenever you want to read the data, then you just go to the index. We tell you which object at which position your entry is, your logical offset is located. So on the stream format, so the stream itself is kind of like controlled by what the index tells you, right? So you can have a WAL file which contains data from multiple streams, but then you might have, say, a Parquet file that was ingested into one shot from directly from the library by passing the brokers, for example, and they all put into order by the index that's kept in Oxia. So, and this kind of like go back to Oxia and what it is. So in this case, it represents the metadata index. First of all, like define what is metadata and what is coordination. But the idea is that we store there everything that is pointers to data, and it's kind of wherever we need any fast access for write and reads in a key value format. And the idea here is that we keep this layer to use like local volumes or EBS volumes, and for having this low latency access. But the size of metadata is several order of magnitudes more than the data. So the point there is that having this gives the flexibility of architecting a system that is much easier to reason about. At the same time, it does not include cost for reading metadata because it is tiny compared to the data itself. So, say, Oxia is a scalable data storage coordination system, and the history also is interesting because we started Oxia as a project to replace Zookeeper. So we have one of the scalability problems in Ursa was Zookeeper, and was from the beginning. Like we could reach 1 million topic, but it was very hard to go beyond 1 million topic. And the first reason was metadata size. Metadata size in Zookeeper, you can get to 2 gigabytes, and then it's kind of like you have to kind of like look at it and be very, very concerned for any single symptom of Zookeeper at that point. So we kind of like design a system that could kind of like remove all these limitations that we had with Zookeeper. And we went to a very different route than what others have done. Like we say, we don't want to implement Paxos or Raft or any other things. They're very tricky to do. And I think that also for Kafka, it took 6 years to get it to production level. K-Raft, I don't know. That's what I've seen, right? So implementing Raft and in a production system is very hard. But the other thing was that it also was implemented, bringing in all the limitations that Zookeeper had, all the architectural limitations that Zookeeper had, like kind of like re-implementing Zookeeper in a different way, in a different place, but taking in all the baggage that Zookeeper had that was not needed for most systems, and that still put the limitations there. So we kind of go through a different route, and first of all, like we wanted to remove all single limitations. So the first idea was that we don't want to design a system for bare metal machines. That's not the environment we are in. We're not deploying into bare metal anymore. We don't have any cluster that we run in production ourselves in bare metal. Everything is based on VM. It can be in public cloud, it can be some private cloud, but it's running on VM and containers. So we can assume Kubernetes as our environment, as our base OS in a way. And we kind of design a system also to have transparent horizontal scalability. Like we want to be able to add more nodes if we are using all the resources of the data cluster. If you need more throughput, we just double the size, and then we have double the throughput. That's it. And it should be quick. It should be instantaneous. operation. Second, that we don't need a global linearizable history like Zookeeper has or etcd, right? That's nice in theory, but it is the main bottleneck, right? You have like every single node needs to have the entire data set. We don't need it. We don't need to have this global linearizable history. We need to have per key linearizable history. That's very important. Or per subset of keys. For subset key, we want to have atomicity, fine, but not for all the keys in the system. And we want to scale up to millions of writers per second, and be able to store hundreds of bytes per second without having to lose our sleep or get paged multiple times. So Oxia is an open source project, so I recommend to check it out. We are already using that in production, so it has been already worked on for a while. And the interesting part is that we designed Oxia for this purpose of replacing Zookeeper in a more scalable way. And down the road, we kind of like figure out that we had other advantages. But first of all, so we have replaced all usage on Zookeepers on Zookeeper for Pulsar and Bookkeeper. So you can from Pulsar 3.2 you can use Pulsar and Bookkeeper without any Zookeeper anymore, and just use Oxia for metadata. And that means that you can now scale up to several millions of topics, and it is very easy to scale up Oxia up and down. You just add more pods in the stateful set, and you have more capacity. And as I was saying, what Oxia means for Ursa. Once we started the designing Oxia, Ursa, sorry, we kind of like, okay, we are using these as a scalable method to store. What can we get out of it? And the nice part of controlling the database is that you can add more features, and you can add the features you need in the most efficient way. For example, like we wanted to have a way to generate offsets that is scalable, that is distributed for a single stream, and that's why we introduced the concept of sequence keys in Oxia. That's kind of like the basis of having multiple writers on a single stream, multiple brokers writing on a single stream, because it is not this broker that is assigning the offsets. It is when writing into Oxia in one single put request, it gets assigned the offset, and therefore you can have multiple brokers writing independently in the same stream, or you can even have a standalone writer getting data from some logs, building up the Packer file and injecting that Packer file into the stream and updating the index. And now the broker will get visible that, oh, I have these new messages available, and I can send it to my consumers in the streaming API. So this is kind of like how we can have these multiple writers, because we have added this feature. Other like we have added partition keys for having multi-key atomic operations, but again, we don't need that across all the keys. We just need it across the keys that we care about. So we can say have for a single partition, for a single stream partition, we want to have some kind of atomicity of the index operations, and we can do that without requiring global linearizable history there. Finally, like to examples here, we have added like floor and ceiling get queries that are not typically in a coordination system, but makes it easy for us to get the highest key in a range of keys. So for example, like we can quickly discover what is the latest committed data in a stream. And at the same time, like when building more and more features, like more complex features that require more data for database like functionalities, we also have added in secondary indices that can let you more easily build application on top of the data store without requiring any atomicity on the. I mean, it is implied that the secondary indices updates are atomic on the database. So this is a bit of the history, like how we started with one goal in mind, and then we kind of like take advantage of that and added more feature in order to support the new requirements. I'm reaching the end of the slides, but before like going to Q&A, I want to also announce that we do have Data Streaming Summit, which is next week or next is on the 29th, I think next week. And so it's in SF. So 28 is mostly training, and 29 is all the sessions and keynotes. So you can use the QR code and go to the Data Streaming Summit. There is all the agenda and the program for the conference. And if you use this LinkedIn 100 code when you register, it is gets free access to the conference. So and there will be all this discussion about Ursa and many other. And also, it's not just about Ursa and Ursa, but there will be also talk from multiple other companies like Uber and Pinterest and others. So if there's any question, I'm happy to answer, or we can.
Thank you. Thank you, Mateo. Questions?
Yeah, hi. Thank you for your talk. I'm pretty interested in Oxia. So, how does Oxia provide fault tolerance with the metadata?
So it is based on there are two layers. First of all, like we do have for data replication, we use a simple log-based replication that is not fault tolerant. So the data is partitioned and in different shards. And if there is a failure, what will happen is that there will be a new leader election. Leader election is kind of like using a cluster checkpointing, and it is using basically Kubernetes config map, which eventually makes a write on etcd. So we kind of use the config map concept that is available to us in Kubernetes as a Paxos implementation that we can use to bootstrap the whole machinery on top of it. So because of that, we don't have to implement Paxos because we have already a config map, and we can use etcd from config map, and that allows us to be kind of to build our replication protocol in a much easier way, because it does not have to be fault tolerant. It doesn't have to be kind of like doing Paxos for each of the round of the data replication. You can just do like a rock-based replication. You have a leader, it flows all the data to followers. If there are failures, the coordinator will elect a new leader.
Okay, yeah, that makes sense. Thank you.
If you go on the GitHub repository, there is a more explanation and more formally define how the replication works, and there is also like a TLA plus model for the whole replication model.
Any more questions online?
Hey, Matthew.
Yeah.
Good to see you. So I have a follow-up question on the index. So for index data, right? So is it persistent or is it in the memory?
Index data, it is persistent. So it is persistent in Oxia, and it is basically it's kind of like a RocksDB like database under the hood.
I see. Alternatively, you can choose to write the indexing information together with your write-ahead log and always recover from that, right?
That was one of the ideas we had in the beginning to like let's just use the object store for that. The problem is that it makes much more difficult to coordinate multiple writers, for example, because like if you have a write-ahead log but now you have multiple people trying to write on the same write-ahead log, so they need some ways of coordinating between themselves, right? And that's kind of like what we're solving by assigning the offset so that each broker or each independent writer that using the standalone library can just append data into the stream by putting an object into S3 and then updating the index. And that updating the index is atomic, so it's kind of, and also it's sequenced, right? So if you try to do that, you write your object, it might take 10 seconds to upload. I write my object. We both try to upload it to update the index. Either you go first or I go first, but that order is finalized there.
Sure. I'm sorry. Shouldn't that be arbitrated by the auxiliary layer?
Sorry, can you repeat?
The sequentializer of multiple writers should be controlled by the auxiliary layer, right?
Yes. So because it doesn't matter that you put the data into S3, the data is not visible yet. The data does not have an offset yet. So it does not belong to the stream yet. It is only belongs once you insert it into the index. At that point, that insertion time, which atomically is one single put, but it's atomic, and we assign the index. Assign the offset, and make this entry visible into the stream.
There's a question online. Vinay Shah asks, you mentioned that a single Pulsar or Ursa cluster can offer both low latency and high latency configuration. What is the advantage of this multi-tenancy approach versus two separate clusters?
It does that you might have so Pulsar itself has been multi-tenant since day zero, right? So we designed this at Yahoo, to have like one single team running one single cluster, and then we had like hundreds of different teams using that cluster. That was very good for like low operational overhead, right? And also like that each team can then just like use the service and not have to like run them themselves. So you don't have hundreds of clusters, you have a handful, you have one or two clusters. Now, repeating the same approach here, it means that you can have your own like logical cluster and then optimize different workloads. You might have like OLTP workloads or more like analytical workloads, but having a single cluster instead of like having tons of different cluster makes it much more easier to first operate and second to discover the data, right? So if you like, if each team they have their own cluster, getting access to that data it is not just a technical problem, it becomes an organizational problem, right? It's like their cluster, their resources, they don't want someone else to come in and read the data because they're putting more loads, they have to kind of operate the cluster. So if you switch that model into a multi-tenant cluster, now it becomes much more easier because there's a shared capacity, and you can see all the data that is there. If you want to get access to some topics, you get like the ACOs, and you get permissions to read that data. You can read the data. It is kind of, that doesn't take any extra effort there. And in reality is that many times there are these different type of workloads like low latency for microservices and all these online stuff and versus analytics. So I think it makes much more sense to have it in a single cluster. And if you don't need the low latency tier, we can just take out the bookkeeper storage layer. But if you need that, and in many cases you will still, then it is much easier to have everything together.
Thank you.
So thanks, Matteo. I also have a question. So it looks like the architecture of Ursa is very similar to what WarpStream is doing. So they also have like a separate controller assigning all the offsets, and then they have the storage tiers sitting in S3 or the object store to lower the costs and so on and so forth. So I'm curious about, what is like the major difference that you see between what WarpStream is doing and and Ursa. And also, do you mind to share some numbers in terms of like latency when you use object store and the latency when you see from the bookkeeper side?
Yes. So there are several differences with the WarpStream approach. First of all, it is called BYOC. I think it's a bit kind of like a different way of doing BYOC, I guess. Like in our clusters, we do BYOC. We have BYOC product. That means that we deploy in your cloud account. We had your permission that everything runs in your account, and there's no. We get the data out of the clusters so that we can give you a dashboard, right? But all the interactions are within your account. Doesn't talk back all the time to our cloud services. In WarpStream case, is all the metadata layer does not run in BYOC mode. it runs in a SaaS mode. That means it will run into warp stream service. So that also means that each time they have to do metadata for each data append, they have to go back to metadata that is on the SaaS side. That also means that the data that you have in your bucket by warp stream, you cannot make any sense of the data if you cannot talk with the SaaS service. So it's kind of like it's your data in your bucket and it's VOC, but if you don't have that access to a SaaS service, you cannot make any sense to it because it's proprietary format there, right? So that is one difference there. I don't think that warp stream targets. I mean, I think we talked with them and they were like kind of like the lowest. They were like, they were targeting work in terms of seconds. And I believe that is because they don't have the concept of write and log, and that kind of like imposes that extra latency in order to have the buffering. In our case, so the number I can give you was that we can reach like to 50 milliseconds on the using S3 regular S3, and the most like 90% of the latency is used by the S3 put request, because using the write log, basically we kind of like the buffering time becomes very close to zero compared to the time it takes to write to S3, because you can write lots of data into many topics, but it still goes to a single write log. So it's a single buffer that you can cut out, and it is very efficient there. So we don't have to do the extra weight there. Using S3 Express, we can reach around 20 millis. Now, S3 Express, it has few caveats, right? It is a single zone, so and it is more costly. So might be make sense for someone, might not make sense for everyone. We are also exploring the way of doing dual writes on S3 Express to have like multiple zones. Again, will increase the cost on more. On the with Bookkeeper, we can reach 2 milliseconds. It's kind of like 220 to 50, kind of like different trade-offs there, right?
Okay, thanks. Yeah, we can discuss offline. I think that some numbers doesn't match what I heard. So yeah, maybe we can discuss offline.
Thank you very much for a very detailed presentation. If you have questions, people can reach you.
Yes, each contact me on LinkedIn or
on LinkedIn. Yeah, I think there is a lot of interesting questions. But let's move on. Thank you very much, Matteo. All right. Our next presenter is our own LinkedIn engineer, Beckett. He will be talking about combining Apache Beam and Flink SQL for stream and batch unification. Beckett is currently a principal staff software engineer at LinkedIn. He started to work on Apache Kafka at LinkedIn after he graduated from Carnegie Mellon University. After that, he joined Alibaba and led the Flink team, focusing on Flink SQL, PyFlink, FlinkML, connectors, among others. He returned to LinkedIn in 2022 to drive the effort of stream and batch unification.
All right. Yeah, thanks, Boris, for the introduction. And hello, everyone. Glad to see you here at our quarterly streams meetup. And my name is Zhang Ji, or you can call me Beckett. And I'm currently working on LinkedIn Streams team, mainly focused on stream and batch unification. So today my talk is going to be about our work that is combining Apache Beam and Apache Flink SQL for stream and batch unification. So that's today's agenda. So I'm going to first introduce a little bit about what does stream and batch unification mean. And then we're going to take a look at our Flink-based solution. And we're going to talk about some caveats of the Beam pipeline API. And then we're going to talk about the solution that we put there in order to overcome the caveats. Okay, without any further ado, so first of all, what is stream and batch unification? You know, on the in a nutshell, you know, for all the data application developers, what they're trying to do is essentially to extract value from their data sets. And in order to do that, they need to use data infra. And as you can see here, the outermost circle here is data application. And the data infra, actually, you can think of them consists of the following categories. So we need to provide a computing engine, and we need to provide the storage infra, and we need to provide a control plane. And in most cases, you also want to sort of provide some data modeling tool. Lastly, there will be a lot of supporting toolings for you to look at metrics, or read the logging, alerting, testing, releasing, and so on and so forth. As you can see today, if you go into each of those categories, the interesting thing is that you will find there are two worlds. One world is called streaming, and the other world is called batch. So these are two completely different ecosystems if you think about it. And the idea of stream and batch unification is to basically bridge those two worlds. We want to simplify. We want to reduce the number of the subjects there. So what we do is that we want to have one single offering for the computing engine, and we want to have one single offering for the storage. Hopefully, also one single offering for the control plane stuff. Maybe it's orchestration, maybe it's workflow, and also for the data modeling and for the supporting toolings as well. So the whole idea here is that we want to break the wall between stream and batch, and we want our end user to not think of stream and batch separately at all. So this is a new design paradigm where people don't need to distinguish between streaming and batch. So that's basically the idea of stream and batch unification. And for today's talk, we're going to focus on the computing engine part. So basically, we're trying to reduce all the engines out there for stream and for batch to just one single engine, which is Apache Flink. So if we zoom in a little bit, what does this exactly mean for stream and batch unification for compute? This basically means we want to have same code, same result, and same experience. So the same code basically means that we want to write the code once and run it on both streaming and batch side. And for the same result part, that basically means given the same input data, the stream and batch job should give you exactly the same result. And for the same experience part, we're trying to achieve where, when you run your streaming job, a batch job, you have the same experience when it comes to logging, metrics, configuration, tuning, debugging, and toolings, etc. So this is basically what we want to achieve for stream and batch unification compute. And our solution is very simple. So if you want to make sure everything is the same, the simplest way to do it is just use one engine, right? So if you have one engine out there for streaming and batch, then you achieve all those goals automatically out of the box. So here in the upper part, this is what we used to have as the stack, the tech stack and linting. So at top tier, we have two APIs are supported. One is Apache Beam Pipeline API, and the second one is Apache Flink SQL API. So, and under the hood, because Apache Beam, we're just using it as an authoring layer. Under the hood, the runners, previously we have two. One is Apache Samza, the other one is Apache Flink. And we are migrating to the following stack for convergence. So we keep the API the same, but we're trying to move away from Samza to migrate to Apache Flink completely, right? So we basically try to just use Apache Flink across the board for the whole workload. As we said, that we want to use Flink for batch and stream unification. So basically that means whether the program is written in Beam or it's written in Flink SQL, we need to be able to run it as either a batch job or a streaming job. So that basically gives us the following four categories. Right? So user may write their SQL statements and they want to run in batch and streaming. It turns out that Flink is super good in terms of Flink SQL. So you can run batch and streaming with a very good performance. So we're happy here. And when it comes to Apache Beam, when you use Flink as an underlying runner, you can actually run reasonably good performance with Flink runner when you author the program in Apache Beam. It's not as good as Flink SQL for many different reasons, but it's sort of acceptable on the streaming side. However, when it comes to the program that is written in Apache Beam, but you want to run it as a batch job, here's where problem comes. So that is basically bringing us to the caveats of the Beam pipeline API. So before we dive deep into why there's a caveats in Beam pipeline API, we need to understand how the API layer sort of work. So on the left side, this is essentially when you talk about a computing engine, it's going to be a typical stack that you will see. So at the very top, you may see a SQL parser, assuming the engine supports SQL statements. So the output of the SQL parser would be a logical plan. And the logical plan will go through this optimizer, by applying a bunch of relational optimization rules. And then you will get this physical plan. And then it goes to the runtime to execute the physical plan. So that's like a very high level sequence of how your job reaching SQL is actually eventually run there. And apparently your SQL statement will work directly at the SQL parser layer. So whatever you write as a SQL statement, it will go through the SQL parser and becomes a logical plan. And there are also declarative programming languages, for example, Spark Data Frame or Flink Table API. They do not go through the SQL parser, but they directly generate the logical plan. And the logical plan still goes through the optimizer. So we call it declarative programming API. And there's one, even lower level API, which is called imperative programming API. And that is essentially Beam pipeline API, Spark RDD, or Flink Data Stream API. So those API directly generates the physical plan. So that plan does not go through the optimizer. So by looking at this diagram, it's kind of very clear why we say, Beam pipeline itself is not a super good fit for the batch workloads. Because it does not go through the optimizer, and it will lose all the benefit that we can get from the optimizer, for example, projection pushdown, filter pushdown, and so on and so forth. Those kind of things are less important for streaming because usually streaming is just processing one record at a time. It's role-based processing, but it turns out to be super important for batch processing because data skipping is actually extremely important for batch processing. That's basically, so this slide basically summarizes what I just said. So because there's no optimizer, we cannot do predicates push down. And there are other optimization rules will be missing. For example, there's join reorder. So you look at the two tables that are trying to join together and you decide, okay, this table is smaller. I'm just going to take this table as the probing side, also as a build side, and I'm going to take the other table as a probing side, right? So those kind of join reorder will also be missing. And also another reason is that, for Beam pipeline API, it's actually working directly to the records format. So this will introduce a much higher SERDI cost compared with binary rows, where you can actually do SERDI on demand at the column level instead of the whole records. It turns out that, because of all those caveats, SQL or a declarative API is a must-have for batch. So that actually brings us to the solution that we came up with. So we're trying to combine Flink SQL with the Beam API. So for the end user who are writing Beam pipelines, we're trying to see if we can help them to accelerate their code, their program a little bit. And before we jump into how can we introduce Flink SQL into the Beam API, we actually need to sort of upgrade the Beam Flink runner a little bit. So previously, what happens is that in the Beam Flink runner, the batch translator and streaming translator are actually separated to different paths. So the batch translator will translate the Beam pipeline into a Flink dataset job. And unfortunately, this Flink dataset API is deprecated already. So we don't want to stay on this. And on the streaming side, it's using streaming translator to translate the pipeline into a Flink data stream API. So the data stream API has been upgraded in the open source Flink to support both streaming and batch. So what we want to do is basically we want to completely remove this path and let the streaming translator to handle both stream and batch jobs. So this is basically what we need to do as a prerequisite for introducing the Flink SQL transform. Yeah. And after that, we want to introduce, actually want to embed the Flink SQL into the Beam pipeline somehow, right? So just to zoom in a little bit on how exactly the Beam will, translate, Beam pipelines are translated into a Flink job. So when you write Beam API, you actually, write a bunch of P streams. And for example, in our case, let's say I'm reading from a Kafka topic and do some transformation, and then I'm writing out to another Kafka topic, right? So this is a very simple Beam pipeline that we can author. And under the hood, what happens is that you will have a P transform start with P begin and generate some, let's say, page view event, right? And then you will have the transform in the middle. That's going to be another P transform. And it's translating the, it's transforming the page view events into, let's say, a page info. Maybe you're just selecting the page info field out of this page view event. And then, the last P transform is ending with a P done. That is essentially you're writing something out, right? So, and under the hood, when the translation happens, so the P transform, the first P transform will eventually become a data stream, Flink data stream of page view event. It's actually highly abstracted, so it's not directly a page view event. It's going to be a window, the value, something page view event. But let's assume it's just page event. And for data stream, the second one, it's going to end up with as a data stream of page info, and eventually you will end up with a data stream of P down. Usually it's a void. It depends on how your writer is written, but typically it's going to be a data stream of void. So this is essentially how a Beam pipeline is translated into a Flink data stream program. And when we want to embed a Flink SQL into it, let's say we want to change transform into as a to a Flink SQL P transform. What we can do is that I put the code here directly. I don't know if people can see it. Hopefully the font is big enough. So what happens is that we want to replace the transform in the as a second step here with something called a SQL P transform. So what we do is that we define a SQL P transform, and we say the input would be, okay, in my case, actually, I put a product class. That basically means the input class. In my previous example, it should be like page event class. And the output class would be country and sales class. And in my previous example, it would be like page info class, right? And what you can do is that then you can call, with DDL. So you can say, I just want to define another table that I can read directly from this SQL P transform without going through the Beam IO. So as you can see here, the product class, that is going to be the main input of this SQL P transform. And that's going to be from the previous P transform's output. And what you can do is that you can define additional input to this P transform by defining DDLs. Yeah, so this with main table, main input table method basically tells, I have some, main input from my previous P transform. And in order to refer to this main input, I want to give it a name, a table name. So that table name is essentially product. And after that, I will have, two tables ready. One is orders, which I directly read from this SQL P transform. And I will have another table, which is called product. That is from the output of my previous or upstream P transform from Beam pipeline. And now with those two tables available, I can write my SQL query directly here. So in this case, we're essentially grouping by the country, and we try to sum the sales. So we have like the country and sales, right? So for the output, what happens is that what we can do is that we can do the following. Sorry, we don't need this output. What you can do is that so ignore this line. It's going to be pipeline to apply Kafka.io with topic product. So remember that this is going to just read the product topic, and then the product topic output is going to be the input for the SQL P transform, which is defined as a product table. And then the transform itself is going to read another table, which is called orders. And then after applying this SQL statement, we will get country and sales, those two columns as a row. And we will insert it into another topic, which is called country and sales. So if we visualize this a little bit on the SQL P transform side, what we can do is that basically we will have some input P collection from the upstream P transform, and we can feed it into this. So the box in the middle, that's the SQL P transform. We can feed it into the SQL P transform, and we can give it a name. We can add additional input tables if we want to the SQL P transform as well from the upstream P collection. And in addition, we can also define the DDL directly. If you don't want to get the input from the upstream P transform, you can also define the DDL. So this SQL P transform will read from the external table directly. And then it goes through a SQL statement. What you can do is that you can specify a main output that is going to be fed into the downstream P transform. And you can also define additional output as well, right? So this is essentially what we did. So we take a SQL P transform and we allow the input to be either upstream P collection or a direct read from the DDL, and you can output multiple data streams as an output, and you can also write directly to the external table if you want to. And in order to make this work, what we need to do is actually we need to be able to convert the Avro records into the row, because SQL only works on top of row format. And all the P collection we have at LinkedIn is based on the Avro records format. So we need to be able to convert Avro to row, and we need to convert Avro, the row back to Avro when it goes back into the other P transforms. So this conversion is not available out of the box in open source Flink. So the open source Flink only supports generic record conversion between row and generic record, Avro generic record, and there are some bugs. So we have to fix that. So there are 2 flips that we submitted in order to fix this. Okay, and just to summarize the pattern that we see here. So imagine this orange box to be the SQL P transform. You can put it into the very beginning of your pipeline. In that case, you can actually leverage this SQL P transform to do all the projection push down, all the filter push down to the original source. So it will, your program will be reading much less data. So it's going to run faster. And you can also put it into the middle. So in this case, what you get is that you will get your computing efficiency. Maybe you're not going to get as much, data skipping benefits, but your computing efficiency will be improved. And you can also read directly from the table without going through the Beam pipeline. And if you put it into the last step of your pipeline, you can also help to just leverage the connector ecosystem available in Flink out of the box, because Beam.io may not have a super rich ecosystem when you want to write something to out, but Flink actually has a very rich connector ecosystem. So depending on where you put your SQL statement, you can actually gain different benefits. Yeah. All right, so this is embedding Flink SQL into a Beam pipeline so that we can help our end user still sticking with Beam, but still write kind of faster code. So the next solution I'm going to talk about is basically we're trying to compile the existing Beam program into Flink SQL with minimal user intervention. And in order to make that happen, we need to first understand when user write a Beam program and they express their logic in different patterns, how can we map all those patterns back to SQL statements? So it turns out that, for Beam, these are the typical patterns you may see, right? You have a map elements, you have flat map elements, and you have a combine function, which help you to reduce n records into one record. And you have like Pardue, which allows you to do pretty much everything, right? So you can map n records to m records, which is stateful. You can leverage the state as well. So now the question is that how can we map all those, things that you can do in Beam back to SQL? So it turns out SQL has UDF, and SQL UDF will allow you to express different semantics as well. So for we should call it like user-defined scalar function. So for the user-defined scalar function, it's stateless. The input is just one row and a few columns. And output will also be one row, but it's just only one column. It only allows you to return one value, essentially. And for user-defined table function, because it's called a table function, now, when the input is the same, you have one row and multiple columns. The output can be multiple rows. Essentially, it's kind of unnesting one record into multiple records. And we also have user-defined aggregate function, UDAF. So it's a stateful function. It allows you to input multiple rows, multiple columns, and output one row, but just one value. So this is UDAF. And if you wish, you can also combine UDAF with UDTF, so that you sort of get n rows in, m rows out semantic, right? So it turns out that we can actually map all those Beam semantic into SQL UDF. Now with this observation, what we can do is that we can wrap Beam functions into SQL functions because they have the same semantic, right? So what we can do is that we can read row into our SQL function wrapper. We convert it into every record. Then we just call the raw Beam function. And then the raw Beam function will return us an every record. We again convert it back to row. And then we output it to the downstream, right? So again, as you can see, you also need this row to every conversion back and forth. So we also need those two flips. The way it works is basically, let's say we have a very simple Beam pipeline, which has read and write. So we will basically convert those read and write call into SQL statements of create table. So that's going to be a DDL, right? For the map and the flat map, we're just going to call it. We're just going to create a temporary. So ignore the create temporary view part, because this is essentially like the glue code that you need in order to create a temporary result for this particular statement. But the key thing is here that what you need to do is that you want to apply this flat map semantic, and the way it works is that you need to lateral join here. So this is how you write flat map in SQL. Essentially, you just write a lateral table. And we put flat map function here, and we're passing argument 1, argument 2, and so on and so forth. So what happens is that we essentially, so this assumes that our upstream is actually a filter. So we read something from the filtered records, then we want to do the flat map. So we're going to just apply this flat map function here. So this is just a very straightforward pattern matching. Right? So are we happy? Sort of, but not exactly. Where are we talking about, the projection push down, right? So one difference between SQL and the Beam API is that all the SQL function, you actually need to pass in one column at a time as the argument, which means that let's say if my record contains 3 fields, right? Name, first name, last name, maybe age. And when you're writing Beam function, you can just pass in this whole record. For example, it's called person. You can say flat map, then person, right? That's it. You pass in the whole record. But in SQL, you cannot do this. in SQL, you have to pass in each field. Right? What you have to do is that I'm going to do a flat map, first name, last name, age. So you need to pass in 3 arguments, 1 column at a time for those SQL statements. Now the question becomes, in order to do projection push down, the whole idea is that for the entire fields contained in these records, maybe only a part of the fields are used, not all the fields are used. So we want to leverage that information to only read the fields that are used by the UDF. We don't want to read the whole record. That's the whole idea of projection push down. Then the question becomes, how do we know what are the fields that is used in the user function, right? Because Beam doesn't tell me this. Just give me the whole person record. I don't know which field in that record is actually used. So this is going to be a problem that we want to solve. So this basically is explaining the problem I just said. So for Beam function, it takes a whole record. But for the SQL function, we actually need the arguments for each column. So what we want to do, well, simplest solution is that you always take all the fields and you pass it to the SQL function. But then you sort of defeat the purpose of projection push down completely. So what we want to do is that we want to ask our end user, what are the fields that you want to use? So we want to basically, there's no magic, right? We cannot, work out of the box, know which fields are used. Maybe we can parse their code, but it's going to be very difficult to do. So as a simplified solution, we just ask them, what are the fields that is used? So they need to return me a list of required fields, name, and the get input class and output class, that's just for the Avro to row conversion, because we need to understand which specific Avro record you want to convert this row to, and back. So, but the key thing is that we want to get the required fields here, and we can also, instead of having this like decorative or fixed in API, we can also ask the user to use annotation. So if we provide a Java annotation, that would also work. Yeah. And now with that information, what we can do is that maybe we're only reading, for example, the first name for the person, but we're actually constructing the full, the partial Avro records. So we have a Avro records object, but with only the first name filled in. And the rest of the fields, we just leave it blank, right? And we pass it to the flat map function. It is okay because the flat map function will only refer to the first name field. It will not refer to the other fields. So in this case, we can actually read much less data. So this is essentially how we translate a existing Beam program into Flink SQL. We map the Beam semantic into SQL semantic. So we basically code jam the SQL statements, and then we wrap the Beam logic into SQL function. And we need additional help from our end user to tell us which fields in your is used in your function, so that we can do the projection push down. Okay, with that, that's all my slides. And thanks a lot. We can, if you have any questions, we can answer that.
Questions?
There's a question online.
Okay, we have a question
Go
in
ahead.
the room as well. Yeah, maybe online question we can take first.
Okay, so the online question is from Rash Singh. Are large network shuffles viable in Flink? With Spark, significant attention and investment has been made into network shuffles for MapReduce type jobs. LinkedIn wrote a custom push-based shuffle engine called Magnet and contributed it to the Spark project. There is also the popular Apache Caliburn project, which operates as an external shuffle engine. Is it viable to implement large network shuffles on a streaming execution engine like Flink?
Okay, so this is a good question. So first of all, yes, the answer is yes. So for Flink, you can actually it can actually work with super large scale shuffle. And but I want to dive a little bit deeper into the question. So there is actually a difference between the shuffle in the streaming side and in the batch side. So in the streaming side, the shuffle is actually pipeline the shuffle. So all the shuffle data won't go to disk. It just, RPC call, then go into some memory queue, and if the memory queue is full, it's back pressured. So this is different from what batch does. So on the batch side, Flink actually does exactly what open source Spark does. So it's called a sorted shuffle. So the sort is it's not based on the key level sorting. It's actually the partition level sorting. So depending on which downstream destination a broker the shuffle data is going to, it's actually basically sorting based on the destination tasks. So that's how it works. So yeah, I think the performance-wise, it's going to be, I wouldn't say very similar. I would say even exactly the same as what open source Spark has out of the box if you use TM Shuffle. But if you want to have like a really good performance, you should also go to external shuffle like Caliborn. So Flink is supported by Caliborn out of the box. So for external shuffle, there are also two flavors. One is mapper view and the other one is reducer view. The difference is that if you want to have a mapper view shuffle, you essentially do not merge the mapper level data together into one file. In that case, if you lose that file, you need to run all the upstream like mapper task again. But the good thing, if you merge them, the good thing is that for the downstream reader, the reducer, it can just read from one file instead of reading from multiple different files and do the merge by themselves. So the other way is that you do the reducer shuffle, which is exactly what I mentioned. So basically, you combine them together, and then if that file is lost, you recompute the whole upstream mapper. But if you do the mapper level shuffle, then the mapper files are actually separate files distributed across the whole shuffle cluster. If you lose one machine in the cluster, you just recompute a part of the upstream mappers. So this is like a trade-off between those two things. And at this point, Flink Shuffle in Caliborn only supports mapper shuffle. It does not support reducer shuffle.
Great presentation. I have two questions.
Sure.
First one is, so it sounds like the entire runtime has been kind of standardized on Flink to a certain extent. And also SQL itself is a very generic language that works for both streaming and batch. Why not just standardize on Flink for everything? And why spending time on this conversion between Beam and Flink? That's kind of first question. And second question, I think everyone is looking into the stream and batch unification. I think in one of your slides, you talk about 3S and so 3 same. I think the second is the same result. I understand from runtime perspective, you can kind of consolidate everything there, but when you're running in a streaming mode versus batch mode, I think there's slightly difference. How do you guarantee that giving you same input that you're able to generate the same result? Like, for example, if the data source is Lakehouse, how do you run streaming and batch? If its data source is a Kafka topic, how does that work? So that's kind of the second question.
Okay, so let me answer the first question. So the first question is that why do we even need the Beam layer, right? So the answer is that it's so first of all, it's a migration, for migration purpose, because we have Samza at this point, and we also want to have Flink under the hood in order for the people to migrate in a much smoother way. We need the Beam layer on top of it. So that's the first thing that we need. And the second thing is that it's also about migration in the sense that we don't want user to completely rewrite their Beam program unless necessary. So because on the streaming side, although the performance is not as good as native Flink API, but sort of acceptable, and we have 80% of the existing programs are still on Beam. So that is why we cannot say, okay, we ditch Beam completely at this point. Yeah. So, okay, and for the second question, basically the question is that we are doing like how do we guarantee the same result between stream and batch jobs? So this boils down to the fundamental design principle of Flink stream and batch unification at runtime. So at runtime, what happens is that for Flink, both stream and batch actually use exact same operator. So there's no difference between the stream operator and batch operator. So they're exactly the same operator. The only difference is that on the batch side, the state backend is replaced to a memory-based state backend. And in order to make sure that we will not hit OM, what happens is that on the input side, all the data set is going to be sorted before feeding to this memory, like in memory state backend. So for example, let's take an example. Let's say I'm doing an addition, right? So let's say I'm doing a sum, basically. And in the streaming world, when you do the sum, because the key actually arrives in random order, what you need to do is that you need to keep this value for each key in the state backend. So your state backend, the key space is actually going to be the number of keys in your stream. So if your number of keys in your stream is like super large, then you will need a big key value map to store it. So that's why your state size would grow. But on the batch side, what essentially happens is that at the runtime, the shuffle layer will sort the whole data before feeding to the aggregation, the sum operator. So what happens is that you will see, let's say, key A, and you may see like 10 records, all are key A. And then you see key B. The moment you see key B, you know that all the records associated with key A has already finished. You will never see key A again. So that basically means you can output the result for key A and just forget about the value associated with key A. So at any given point, you're only keeping the state of a single key in your in-memory state backend. So that is how you make sure that you're not going to run out of memory on the batch side. But as you can see from operator's perspective, it doesn't know anything. It just has exact same processing logic. It reads from a bunch of data like one at a time. The only difference is that now you sort of know at the point when you see a different key, you can discard the value of the previous key, right? So this is how Flink actually guarantees the same result in stream and batch. And you also mentioned that let's say you have a Lakehouse as a source and you have Kafka as a source. So typically you will not run a streaming job against Lakehouse, and you will not run a batch job against Kafka, mainly because Kafka lacks a lot of capability compared with Lakehouse in terms of like all the data skipping indexes there. So there's no projection pushdown, there's no filter pushdown. You basically have to read everything sequentially. So this is going to be very slow. But if you're reading the same data from Kafka, let's say I have a streaming job reading the same data from Kafka, and I ETL the same data to Lakehouse and I read from that Lakehouse table, as long as the data, the records enters Flink are the same, then the result is guaranteed to be the same. One caveat on the streaming side is that potentially if you have a windowed state, potentially you need to handle like super late arrival data. And you may need to keep your state for very, very long. Your state may grow. So one prerequisite for the same result would be you actually can handle all the late arrivals on the streaming side. So this is actually one of the, I would say, ongoing evolution in the streaming area where people want to have infinite state. So we will see like all the trends of evolving the state backend from local state backend to something like tiered state backend, right? So you will have like infinite storage on the secondary storage. So you can actually recall all the states, even if it's a long time ago. Maybe it's going to be a little bit slower than what you have in the local state, but you can still recall that. So this is going to be, I think, it's going to be a pattern changing design for stream processing as well. So infinite state.
All right. Thank you very much, Beckett. If you have any questions, you can reach out to Beckett. the Meetup page has like its email, right? All right, thank you very much, everyone, and good night. There's still some food left.